Okay, so good morning and welcome to the opening plenary session of Loops 2024. Our first speaker is Thomas Thiemann from the Friedrich Alexander University at Erlangen. Thomas has made seminal contributions to deep foundational issues in loop quantum gravity. He has mentored generations of outstanding students at Erlangen, and he has written a beautiful monograph on Hamiltonian LQG, which has quickly acquired the status of an indispensable reference in the field. The title of his talk is Backgrounds, Perturbations, and Reduction in Canonical Quantum Gravity. So, Thomas, the floor is yours. The total time, including questions, is 40 minutes. The recommendation is 30 plus 10, but as long as it's all 40 minutes, that's good.
Yeah, thanks, Madhavan, and thanks to the organizers for the opportunity to speak at this conference. So my job, as assigned by the organizers, is to give an overview of the topic canonical quantum gravity, in particular loop quantum gravity in the canonical framework. So I will be this will be an overview talk for most of the time, but there will be also some new things that I will say towards the end of the talk. So here's my table of contents. So I will first summarize what the task of canonical quantization of quantum gravity is all about. Then I will briefly say what is the status in the implementation that we know as loop quantum gravity. And then I close with an outlook, summarizing and giving some new ideas. So the canonical approach to classical and quantum gravity is quite old. It has a long tradition. In the classical side, we have the initial value formulation, numerical integration of Einstein's equations, black hole merger simulations, and so on and so forth. Also, on the quantum side, quantum gravity has been formulated as a constrained quantum field theory by the founders of the field a long time ago. The key assumption is that we have a well-posed initial value formulation, which leads you to globally hyperbolic spacetimes, which necessarily have a product structure. So you can foliate the spacetime by spatial leaves, which are known as Cauchy surfaces, and this is known as the 3+1 formulation. And since you then have a 3+1 space-time split, you can, as usual in field theory, go from the Lagrangian to the Hamiltonian formulation for forming a Legendre transformation. That Legendre transformation is singular, and you have in next to momenta and coordinates, you also have constraints, initial value constraints, and you have Poisson brackets. So Q and P are in what follows the 3 metric and its conjugate momentum. So here this is my notation for the initial value constraints, the vector constraint, and the scalar constraint, also known as spatial diffeomorphism and Hamiltonian constraint. A key object in all of this is the determinant of this spatial metric. It will come up in the various places in what follows. The smeared constraints, so I'm smearing the vector constraint against the scalar field, sometimes called the shift vector field, and the scalar constraint is smeared against the scalar function called f, sometimes called the Labs function. And these constraints, they necessarily form a Poisson algebra, which is known as the hypersurface deformation algebra. That algebra encodes local spacetime diffeomorphism covariance. It is ill-defined for degenerate metrics, so it's very important in the classical theory that Q is different from 0. And it is not a Lie algebra because the structure, what usually would be here is a structure constant on the phase space. It's no longer a constant because of the dependence on the spatial metric in this on the right-hand side. And an anomaly-free representation of this algebra in the quantum theory is a major challenge in canonical quantum gravity. So another classically equivalent formulation is the so-called reduced phase space approach. So for simplicity in this talk, I will focus on spatial manifolds which are free of boundaries so that I don't have to talk about boundary terms. So I will abbreviate my formulation and call a test function capital T naught be the scalar part, and TA equals UA, the vector field part. So my constraints will be just conveniently written now in terms of this 4-dimensional notation. And then what you do, you split your canonical pair into two parts. Q and capital Q and P are the so-called true degrees of freedom, and X and Y are the so-called gauge degrees of freedom. You solve the constraints for the gauge momentum, Y. You impose some gauge fixing condition on so that should be an X here in the gauge condition, should be an X instead of an Q. And then you also here you should have an X here. You impose the stability of the gauge. And the reduced or physical or true Hamiltonian is then that phase space function on which delivers the same equations of motion for functions of the 2 degrees of freedom as the constraint linear combination of constraints does when you go to the constraint surface, when you impose the gauge fixing condition, and when you impose the stabilization of the gauge fixing condition. And whether or not that is practically implementable depends very much on the matter content that you have. Now we come to quantization. I will discuss here 3 qualifiers, which also appeared in the title of my talk. Background independence means, generally speaking, that there's no auxiliary structures, for example, a background metric. Non-perturbative refers to the fact that we don't do a graviton expansion in the perturbation around G0. And quantum reduction means that we solve the constraints after quantization. The respective opposites are then background dependent, perturbative, and classical reduction. We note that a perturbative approach implies that you automatically have a background dependence, or in other words, negating this logical implication that background independence means that you are automatically non-perturbative. Perturbative approach has been applied to quantum gravity a long time ago and turned out to result in a non-renormalizable theory. Therefore, perturbation theory seems to be ruled out. But on the other hand, we note that an implication is not an equivalence relation. Therefore, we can have actually a background-dependent formulation without going perturbative. So this will be important in the last part of my talk. Still, most approaches in quantum gravity prefer a background-independent approach, like asymptotic safety, causal dynamical triangulations, canonical quantum gravity, causal sets, and even string theory in the ADS CFT formulation. So what do we mean by canonical quantization? Canonical quantization means that we select a Weil algebra either for when you do the constraint reduction and quantum reduction in terms of this full phase space, or when you do the classical reduction in terms of the true phase space. You formulate a Weil algebra. You express either the constraints or the physical Hamiltonian in terms of elements of that Weil algebra. You study states, i.e. Expectation value functionals on that Weil algebra, giving you the so-called GNS data, a representation, a Hilbert space, and a cyclic vector, such that the constraints and even their algebra is densely defined on this dense domain of the Hilbert space. And if you have a Hamiltonian, you want that Hamiltonian to be densely defined. In addition, if you do the quantum reduction path, then you want that these operators, rho of C of T of the constraints, obey the hypersurface deformation algebra without any anomaly. In the classical reduction case, you want that the Hamiltonian has self-adjoint extensions. The classical reduction path gives you then a Hilbert space, which is already the physical Hilbert space, and you can immediately go on and study the S matrix elements of your generated by the Hamiltonian. In the quantum reduction part, you have to do more work. So you have to construct solutions which are linear functionals from that dense subspace into the complex numbers, such that when you apply a constraint operator to an element in that dense subspace and evaluate the solution on it, you get 0. If the constraints actually form a Lie algebra, then there's also a so-called rigging map, which allows you to construct a physical inner product. Unfortunately, this is not the case for quantum gravity, because our algebra is not a Lie algebra, it's something more complicated. It's an algebroid, as I indicated on the first slide of my talk. And even then, you are not done, because you still have to construct a new representation of gauge-invariant observables, also known as Dirac observables. So we see already that the quantum reduction path is much more complicated than the classical reduction path. So now we come to the implementation in loop quantum gravity. So first, the kinematics. Since we want to discuss the coupling of spinorial matter, it is motivated to go to a triad formulation rather than a three-metric formulation. And then you can use Ashtika-Barbero variables and talk about the conjugate momentum, conjugate to this densitized triad, which turns out to be an SU2 connection. Therefore, you have an additional Gauss constraint next to the spatial diffeomorphism and Hamiltonian constraint. And one notices that every term in the Gauss constraint or in the initial value constraints has at least one factor of E of this densitized triad. Therefore, it is very well motivated to choose a state such that its cyclic vector is killed by E, by this electric field. Which means, of course, that this vector is a degenerate vacuum state. It's quantum degenerate. And this kind of requirement then already gives rise to a state which is irregular. Irregular means that at least one of the while operators is not strongly continuous. So you can, for example, have, as in loop quantum gravity, we can talk about polynomials of the E operator, of the smeared E operator, but you don't have polynomials of the A operator. You can only talk about holonomies, exponentiated A operators. Nevertheless, you can get very far with this. So there's this kind of state, the LQD state, which is defined by this very brief formula, is equivalent to the following statement. The GNS representation that you get from the state is the famous Ashtika-Isham-Lewandowski Hilbert space representation. It has an orthonormal basis, first given by Bayes, Rovelli, and Smolin, now known as the spin network function basis, and is actually the unique diffeomorphism invariant state on the Weil algebra formed by holonomy fluxes. Now about the dynamics in loop quantum gravity. We consider now representation of the Gauss constraint. It turns out to be densely defined already, and we can actually explicitly solve it in terms of the SU2 invariant intertwiners, which is basically known to everybody since his first days in quantum mechanics, because you just need to combine in invariant way in Clebsch-Gordon coefficients. Also, the exponentiated spatial diffeomorphism constraint is densely defined, and also the solution space in this case can be explicitly constructed in terms of so-called spatial diffeomorphism invariant distributions. However, the scalar constraint or Hamiltonian constraint remains a major challenge, and this can be traced back to the fact that the operator A of F by itself does not exist. What exists is only the holonomy of this operator. So there is actually a densely defined version of this operator, which is obtained by a limiting process which involves this diffeomorphism invariant distribution space, but it suffers from ambiguities, and it is not anomaly free, in the sense that the commutator can be computed, but it's not equal to the quantization of the classical Poisson bracket. Nevertheless, it's mathematically consistent in the sense that this commutator kills diffeomorphism invariant states. That is at least consistent in the sense that on the classical side, in the classical theory, the Poisson bracket is proportional to a spatial diffeomorphism. So at least that is true. People have thought about improvements. There's in chronological order, there's the master constraint program, which replaces an infinite number of these constraints by a squared sum of those. The advantage is that now you have only one constraint, therefore it has a trivial algebra. There cannot be any anomaly, and a rigging map is available. And there's the habitat construction, which goes long way back to this paper by Gambini, Mara, von Pullin, and Lewandowski, and has been improved by, in particular, by Maratarian. So here you choose a space much bigger than the spatial diffeomorphism invariant distributions, and you make sure that the limit now can also be taken, and that you, in this case, you can show that you can, at least for Euclidean vacuum general relativity, you can derive an algebra of such dual constraints, as one calls them, which is non-anomalous, and that also the ambiguities are reduced. However, all three proposals still suffer from quantization in ambiguities, again due to this non-regularity of the state, and the physical Hilbert space is likely not to be separable. About the classical reduction path, it turns out that most of the work that has been done in this direction uses a certain matter which is known as dust matter. It has been introduced by Baum, Kukash, and Tore, and later used for quantization in purposes in loop quantum gravity. What this matter does is that effectively the reduced Hamiltonian or physical Hamiltonian becomes a function of the initial value constraints, which have not to all of these constraints, but only to the geometry and non-dust matter part of the Hamiltonian and spatial diffeomorphism constraint. Therefore, these constraints, but this part of the constraint is therefore no longer constrained to vanish. The advantage is that, as I said before, that kinematical Hilbert space is the physical Hilbert space already. However, since then this kinematical Hilbert space is the physical Hilbert space, it's of course again not separable. And the Hamiltonian, while it can be now defined similarly on the dense subspace, it suffers again from quantization ambiguities. These kind of ambiguities are also there in truncated models of the theory, like, for example, in loop quantum cosmology, or the loop quantum cosmology like treatment of the black hole interior. The good thing is, at least we do not have to worry about solving the constraints and representing observables, but nevertheless, unfortunately, we still have ambiguities, and to make reliable predictions, which we all of us would love to do, we need to fix those ambiguities. For example, by renormalization, as has been emphasized by many people, in particular Bianca. So given these complications, so now I'm entering the last part of my talk already. Given these complications that originate from the irregularity of the loop quantum gravity states, which results in these ambiguities and the non-separability of the Hilbert space, one can ask what other options exist. And this goes back now to the beginning of my talk. So I remind you that background dependence does not mean that I go perturbative. Like, how far in particular can we push regular background dependent Fock states? And I would like to start this part of my talk with a quote from a physicist who is known or famous for his sarcasm, namely Sidney Coleman, who said once that the career of a young theoretical physicist consists of treating the harmonic oscillator in ever-increasing levels of abstraction. And what I discovered for myself is this: the career of a more senior theoretical physicist includes treating the harmonic oscillator in ever-increasing levels of abstraction. So here goes the last parts of my talk. So we have insisted so far that the constraint operator, the representative of the constraints in the quantity, is actually an operator acting on a dense invariant domain. And there's a good reason for that, because we want to compute commutators of these quantum objects in such a way that linear functionals which act on this dense subspace can also act on this object rho of C of t applied to an element of that dense subspace. So you can do that once, and you want to do it twice in order to compute the commutator. So now let us now consider such a linear functional, and let Vn be an orthonormal basis taken from this dense subspace. For example, the spin network functions in loop quantum gravity. Then the linear functional is uniquely defined by the numbers given by the evaluation of the linear functional on the basis states. Therefore, you can write such a formula formally that the linear functional is just the linear combination of this dual states, this bra states Bn, multiplied by these complex numbers. Then L is a solution if and only if L applied to rho of C of t times B of m, which can be expanded in this way, is equal to 0 for all possible m and for all t. But now we see that this curious fact that this object in the middle here involves only the matrix elements of rho of C of t. So in other words, in order to write this formula, it is completely sufficient that rho of C of t is not necessarily an operator, but only something of which I can compute the matrix elements. Such a thing is called a quadratic form. So the constraint condition that I wrote up here is also meaningful if rho of C of t is just a quadratic form, not necessarily an operator. So now let us consider a Fock representation of our Weil algebra and consider the constraints normal ordered with respect to the corresponding annihilation and creation operators. Then it turns out that if the constraint is written in a polynomial way, which we can always do by multiplying this by a sufficient power of the determinant of Q, then rho of C of t is immediately in density defined quadratic form on the dense span of Fock states. The advantage is that such the corresponding expectation value state with respect to Fock vacuum gives rise to a separable Hilbert space, and its quantization ambiguities, or the quantization ambiguities of quadratic forms or even operators, are heavily reduced, because usually things turn out to be well defined only if you use a very specific order, which is known as the normal order. And the state is irregular because I can talk about both smeared electric field and I can talk about the smeared connection rather than the holonomy. The disadvantage is, of course, that quadratic forms cannot be multiplied. They behave a little bit similar to distributions. You can evaluate distributions linearly, but you cannot multiply distributions in general. And now comes the question, while it is true that I cannot talk about the product of quadratic forms, is it possible to actually define something like a commutator of quadratic forms? Because there's a minus sign, right? I'm talking about rho of C of t times rho of C of t prime minus the opposite. So the minus sign can lead to cancellations, and it could just happen that the number of cancellations is just sufficient to make this turn this into a new quadratic form. And to answer this question in controlled way, we use non-perturbative methods from constructive quantum field theory. I was in particular inspired by the Glimpse, very beautiful paper on the construction of phi to the fourth theory in 3 dimensions. So we introduce on the one particle Hilbert space a basis of one particle Hilbert space vectors, which are called usually modes. If you take, for example, in terms of the usual Fock spaces in quantum field theory on Minkowski space, these are labeled by momentum vectors, but this is not necessary. It can be any label, and you can impose cutoffs on that label. For example, a momentum cutoff, and the notion of convergence for quadratic forms is the weak operator topology, so matrix element convergence. And now it turns out that if you impose such a cutoff on the modes and use that cutoff to control a quadratic form, then the weak limit of that quadratic form is exactly the quadratic form on the Fock space, which is well defined that we started from. So any such truncation in terms of modes gives you back what you started from. And then these quadratic forms are now, when truncated, are actually operators with dense and invariant domain. So this commutator can now be computed in a controlled way. And now we define the commutator of quadratic forms, if it exists, by any weak limit of this commutator, and whether it exists or not depends on how you take these cutoffs to infinity. And the astonishing thing is now that if I do this for the HTK-Barbero variables with the density 2 polynomial constraints for the scalar constraint, which has polynomial degree 4, then I can find a limiting pattern sending the cutoffs to infinity such that the algebra is represented without anomaly. And the proof is very long, but straightforward, and it just uses harmonic oscillator algebra. And this is why I quoted Sidney Coleman. In the Lorentzian regime, you can, in principle, use the same technique, but its computation is much harder because we have now, in order to turn this into a polynomial, we have to work with polynomial degree 10 and density weight 6. And the phenomenon which seems to be at work here is very similar to spontaneous symmetry breaking. So if you think about the algebra as analogous to a Hamiltonian in the spontaneous symmetry breaking scenario, then while the Hamiltonian is symmetric, the ground state does not need to be symmetric. So in our case, the ground state is represented by this Fock representation, which is heavily background dependent and certainly not symmetric in any case, in any sense. Now we go to the reduction path, so classical reduction. So we talk about Hamiltonian rather than constraints. Again, I want to highlight the importance of this object, the determinant of the metric. It enters the reduced Hamiltonian with negative powers, and it also enters geometrical operators or geometrical quadratic forms with negative powers. So to make the discussion as short as possible, let me consider for example, for simplicity, the QP polarization. So I talk about free metrics and conjugate momentum. Then we have the following result. Let us work in any spatial dimension capital D. Let us consider any little d-dimensional object, like if I'm in 3 dimensions, like this could be a curve, a surface, or a region in this 3-dimensional space. And let us think of this surface as embedded y, an embedding y. Then for any integer, not necessarily positive, it can be negative, any positive or negative integer. This object can be defined as a quadratic form on the Fock space, but for every quadratic form, you also have to specify a domain, and the domain is not the linear span or the excitations of the Fock vacuum, but actually the excitations of a coherent state labeled by a non-degenerate metric. On the same domain, then therefore you can define a quadratic form corresponding to the volume of. So I think I was at this point, or this. I think this is the last thing I could say before the connection got lost. So the also you can define therefore the thing that we love very much in loop quantum gravity, namely a quadratic form corresponding to length, area, and volume. And the coherent state expectation value is exactly the volume of S assigned by the coherent state. With the same technique, you can also define quadratic forms corresponding to the Hamiltonian, the reduced Hamiltonian, or the master constraint. And it's nice to see that there's an imprint of the classical hypersurface deformation algebra, which requires that we talk about non-degenerate metrics, is here incarnated in the condition that the domain of these quadratic forms is not arbitrary, but it has to be, for example, based on the excitations of a coherent state with non-degenerate metric underlying it. And notice that everything is heavily background dependent, yet manifestly non-perturbative. So let me summarize and leave more time for questions. So once again, the quantum reduction approach is much more involved than the classical reduction approach. And surprisingly, at least to me, this was very surprising, is that Fock states perform much better than expected. If you forget about the Hamiltonian constraint, you can go even much further and study more general representations of just the spatial diffeomorphism constraint. And there you can find actually background independent Fock representations such that the vector or spatial diffeomorphism constraints is not just a quadratic form, but even a self-adjoint operator. So to put it in short terms, the LQG state, its advantages are, of course, that it's background independent, is actually an operator rather than just a quadratic form. But on the other hand, it leads to ambiguities because of the irregularity of the state, and in a sense, we are very far away from the quantum field theory and curved spacetime formulation. And the Fock states are performing in the opposite direction, so they lead to separable Hilbert spaces, minimize ambiguities, and are very close to quantum field theory and curved spacetime. But on the other hand, at least at the moment, for example, the reduced Hamiltonian is only a quadratic form, not a operator. Notice in that respect, I think I forgot to say that that not even the standard model Hamiltonian for the usual particle physics on Minkowski space is actually an operator. It's also just a quadratic form. And I think that improvement on both approaches can be done using these constructive quantum field theory techniques, in particular renormalization. So thanks very much for your attention. I cannot hear anything now.
Yeah, thanks a lot, Thomas. Can you hear me?
Yes, I can hear you.
Yeah, so thanks for a wonderful talk and for completing it exactly on time. So now we have lots of time for questions, around 10 minutes. I think Abhay had a question.
Right.
In front over here. You have a mic?
Sure, yeah, I have a mic. Yeah. So Thomas, I'm very confused about your philosophy here. I mean, you know, for years you sort of worked with background independence, and here when you talk plus or minus, I mean, I thought a huge minus would be for the Fox state that it is background dependent. You say that very, you know, very briefly, but so first of all, I mean, what is the background that you're choosing? You're just introducing a flat metric by hand as a background, and
Yeah, so I mean, this topic, of course, deserves a whole talk by itself. But yeah, and for example, the background dependence could be an auxiliary metric that you introduce, which has Euclidean signature, and then you use that metric in order to define a Fock representation. You introduce, for example, Laplacian based on this metric and so on and so forth in the usual way.
okay, but I mean, many times you say curved space-time. It's not curved space-time, right? Because in curved space-times in general, there is no Fock representation. I mean, there's no canonical Fock representation. There are infinitely many which are unitarily inequivalent.
Yes, that's true. That's true.
So, I mean, so it's not really curved space-time. It's really, you're choosing a flat space. I mean, Euclidean. By Euclidean, you mean not just plus, 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 but flat.
No, I mean, no, it can be curved spacetime.
But then there is no canonical Fock representation.
Why? I mean, there's no distinguished one, but I can.
Yeah, but they're unitarily inequivalent even. So I mean, the ambiguity, then you should have another minus there about there is a huge, you know.
It's the same. It's the same minus that you have for quantum theory in curved spacetime.
Okay, thank you.
Daniele?
Yeah. Hi, Thomas.
Hi.
I was wondering if there is a relation between the background-dependent construction you give and the non-degenerate condensate vacuum that Hanno and Tim have constructed.
The philosophy is similar, but the kind of state that Hanno and Tim were inventing still leads to a representation which is not regular for both variables.
Because in that case, you wouldn't need any auxiliary metric to construct the Fock state. You would directly use the background corresponding to the non-degenerate vacuum.
Well, you also have to specify a background in their construction.
Okay, thanks.
This defines the condensate or the classical metric that everything is somehow close to.
Yeah, please go ahead.
Okay, it might be a naive question, but thinking in the standard Stone von Neumann terms, is Hilbert space separability directly related to quantization ambiguities?
It's not that one implies the other necessarily, but when you have a non-separable Hilbert space, then in general you need to discuss this topic, which is called super selection sectors. So here you enter into a discussion of how to choose that super selection sector and so on and so forth. In that sense, it leads to ambiguities.
Okay, thank you.
Any more questions? Yeah, please go ahead. Oh, is there a question? No? Okay, if there are no more questions, Thomas, I have a question. So is this of any direct use in trying to ameliorate some of the problems with generalizing the R-Fock representation to the non-abelian situation?
So this whole thing was driven by the question, in fact, by your kind of work. Like you were very much interested in finding non-anomalous representations of the hypersurface deformation algebra. So I was wondering, since you are working on kind of dual space, whether where you also, in some sense, work in terms of matrix elements, where the bra is more like a distribution rather than a state. Whether this can be seen also in the usual sense of quadratic forms. So the whole subject started with asking the question: can one do this also in a regular representation? For example, a fork representation, not necessarily a fork representation, but this is a good example. And it turns out, surprisingly, that the answer is yes. And whether it has anything to do with the R fork representation, I think the R fork representation is in a sense a usual fork representation that does that you specify very specifically how the smearing function is related to an abelian holonomy. And here the non-abelian case can be also treated, but in the sense that one also has to discuss the quantization of the Gauss constraint. And one does this without going to holonomies.
I see.
So I never have to talk about like path ordering, for example.
Okay. Thanks a lot, Thomas. So there is a question.
I have a question here.
Ivan?
Hi. My question is whether the concrete choice of background metric that you use to build this focus space limits the physical applicability of the theory somehow, or not, or is just a fiducial structure that you need to choose to build the theory, but then you can apply it. And in particular, I am thinking about inequivalent representations.
Yeah, so this question is related to our bias question. The background comes here in two places. First place is in actually the choice of the representation. And the second place is in the choice of the cyclic vector that you build your excitations on. These two can be the same, but it can be different. It's up to you. But I expect that it will be very advantageous to choose the two equal to each other, because otherwise the operators that you discuss will be more singular than when you don't make them coincide. So when you have made that coincident choice, you're back to the question, which representation should we choose? And this is a kind of question that people in quantum field theory and curve space also discuss, where they use physical arguments to reduce the choice, or the class of choices that you want to make, known as the Hadamard condition, which similar to what I'm doing here, in the sense that this also is a condition which makes sure that the stress energy tensor is a well-defined quadratic form. So yeah, so I would say that there will be restrictions of that kind, but you will never pinpoint exactly one representation. You may want to pinpoint a class of representations which are known in the volume of a certain one. I think this is the best one can do.
Last question, Alejandro.
Hi, Thomas. So I'm also very confused, just as a pie. So if you are going to go back to a Fock representation, independently of which one and so on, so then why the need of even having holonomies, triads, and so on? You could just do it in old geometrodynamics, right? So
that's what I did. Exactly, this is what I did here in this slide. Okay. So you don't need to exponentiate. You can actually use the 3 metric and its conjugate momentum as it is, as a polynomial. This is the advantage. I mean, this is, so this kind of question came up because when you have holonomies, you cannot talk about A of f. You can only talk about the holonomy of A of f. And whatever operator you have to approximate it in terms of holonomies. And how the way you do it is not given to you. It's not God given to you. You may be able to restrict it somehow by asking that certain algebra of constraints is closing, but there will be ambiguities, and I want to get rid of these ambiguities. That's the motivation behind of all this.
So thank you, Thomas. Let's thank the speaker again.
Thanks.